If we start DC nail and create a new project, you see, like in most of the other programs, we have the most important functions at the left side. For those who already know our programs, this is just the latest version released yesterday with a new layout, with a consistent color scheme, and with Windows 10 layout of all these icons and pictures, which is very new for all the DC software programs. So we have the most important functions here under these icons at the left. And first, very important is the analysis standard where you want to work with. Here we have some older standards like German analysis standards of 1967 and 2005. We have the Swiss code SA 267 for Switzerland, and we have Eurocode 7 with quite a number of predefined national annexes. Here you see the selection of Austria, France, Great Britain, and Italy. And we have as well the option to define a free definition. So if you need a national annex for Czech Republic or whatever, you can define here which settings you will need, which national annex parameters, which safety factors, design approach 1, 2, or 3, and you can define your annex under one of these 3 buttons here. We will keep German here, and you see that all these parameters are predefined, so where to define which parameters. And as well for the design of the shotcrete wall, here we have Eurocode 2, and as well we select the national annex of Germany. Now we have a permanent construction, for example, and we start with the input of the ground surface, the original ground surface without any excavation. So we can have here some shape. What is special here with DC nail, as a difference to DC pit, for example, is that we don't have the classic earth pressure calculation, which only uses horizontal soil layers. But in this program, DC nail, we have the earth pressure calculation according to Kuhlmann, which allows arbitrary shapes of the ground surface and of the soil layers. So I define this ground surface here, and when I stop this input with the right mouse button, I can define the parameters of the first soil layer and can enter the name, angle of internal friction, cohesion, unit weight, and so on. Or we can use a parameter suggestion. So if you have the same types of soil layers again and again, you can predefine these parameters here. For example, sand mellow has an angle of internal friction of 30 degrees, no cohesion, unit weight of 18, and so on. So these parameters are entered here. And we have one special parameter here for DC nail, which is the so-called limit shear force, which tells us how much force can be transferred per meter nail into the soil. So this limit shear force can be calculated and is based on the skin friction in a certain kind of soil layer, for example, 120 kilonewtons per square meter. And the press unit, the fixed length of the nails, has a diameter, for example, of 60 millimeters. So this skin friction multiplied by the circumference of the press unit gives this limit shear force, so we can transfer 22 kilonewtons per meter length of any nail from the nail to the ground. We have also the option to consider specific joint planes. If we have a rock with a certain inclination of joint planes, we can predefine this. So this is calculated in addition. But here we have a normal ground surface, normal soil with these parameters. So we just click OK for the ground surface here. We can then have different other soil layers. Here, for example, there should be some clay with a phi of 22.5 degrees and a cohesion of 5, for example, and so on. So we have different soil layers with an arbitrary shape. We can define a water level in the ground. And then, if we have an excavation at this side, we define the shotcrete wall, which holds the surface here and which is fixed by the soil nails. So I can enter the wall here. Mostly it's inclined, for example, under 80 degrees. And these can also several sections, or I finish this with the right mouse button. And then we have the parameters for the shotcrete wall. We have the thickness of the wall, the edge distance of the reinforcement axis for the excavated size and for the supported size. If we have only one layer of reinforcement, we can enter the parameters in a way that the sum of both is equal to the thickness of the wall. So we have, in this case, we have only one layer of reinforcement. And if these values are smaller, we have two layers for the excavated and supported side. So concrete grade, Young's modulus, the strength of the steel, and so on. So these are the parameters of this wall. And now we see this is cut off here. Here, this is the excavated side, where we'll have later the excavation stages. And these colors are used if they are predefined. Under settings, we have a so-called symbol editor. And here, any soil name may be defined with a short designation G only for gravel or a long text. And this gravel can have a color yellow. And if the defined soil name, here sand, for example, is found in this soil editor, in the symbol editor, then the color is used to display the specific soil layer here. Now, after the shotcrete wall, we define the first layer of soil nails. So, for example, here at this position, with a certain inclination, this should be, for example, at a depth of 0.5 meter. We can define the minimum length of the soil nails. Mostly this is a minimum of 3 meters. We have a certain inclination of the nails. Usually they are rectangular to the shotcrete wall. So this would be an inclination of about 10 degrees here. If we use soil nails and anchors, where the anchors have a larger fixed length, larger diameter, we can define a factor here, which is specially used for this anchor. We have a horizontal spacing of the soil nails. This is usually 1.5 meters, and the strength of the nail steel. Now, with this construction for soil nailing, we often have quite a number of excavation stages and quite a number of nail layers. So we can enter this with an automatic function. For example, I can select here to create the corresponding excavation with 0.5 meter below this nail layer. And I want to have, for example, 6 additional excavation stages, all with a difference of 1 meter in depth below the last one. So if I enter these options here, the program asks for the parameters of the excavation. For example, E1 is the first one. Usually we have to excavate one step, and then we can enter the soil nail. So while we have the excavation, the soil nail, the last layer of soil nails, is not yet active. So consider last nail by default is switched off. I can show you the effect a little later. So usually all the nails below and with the current nail layer are lengthened if it is required for the stability. So if I confirm here the excavation stage, all the stages are defined automatically. So we have in total 7 excavation stages and 7 nail layers. And in each excavation stage, we have switched off to consider the last nail. So we first have to excavate here and can then enter this nail layer. So finally, we need one excavation stage where the last nail is acting. So for example, I can copy here with copy and paste. I copy this excavation stage. I place it here a little higher. And if I edit excavation stage 7, this should be a little higher, 6.9 meters, for example. And the last excavation stage, E8, should consider the last nail. So in this last stage, the last nail layer is present. So we have now 2 different stages. I forgot to enter the depth. So here at -7, and the next point should as well be -7. I need a difference between the different excavation stages here. So there is 1 point too much here. So this should be -7. Okay. So we have our soil layers, we have our excavation stages, and we can enter different types of loads. They may be concentrated loads and distributed loads. Here, for example, along the ground surface, we can have a live load of 10 kilonewtons per square meter. We can have a point loads at another position here, for example, 50 kilonewtons. And all the loads which have the same load case are calculated together in one step. So we could enter one specific predefined unit of failure, which is calculated in addition to check if this is the critical one. Then for the slip circle, for the ground stability analysis, we could add a fixed point to make the calculation a little faster. And we have some important options for under project analysis and output. Here we can select if we want to have the slope stability analysis only in the final excavation stage or in every excavation. And one detail might be helpful if you have a very steep slope here with a certain distance to the nail wall. The critical slip circle might be in this slope here, for example, but this is not what we want to calculate. We want to calculate the slope stability for the complete soil nail analysis, so we can check not outside the wall area. So no slip circle here in this slope, for example, is calculated, but only slip circles which cover the soil nailing construction here. Now we can calculate the situation, and we see here the iteration of the different blocks. This is a so-called kinematic element analysis, which looks for a critical block with the least safety. And in addition, we make a calculation of the slope stability analysis. And now we can check the graphics for the different excavation stages. And for example, in the first stage, we don't have any soil nail yet, because this has to be introduced after the first excavation. So at this point, we have a safety factor of 0 because we have no nail forces. So this small block of ground must be stable for itself. And then in the next stages, we have our nails, which need a certain force to stabilize this block. And we have, or we need, safety factor greater than 1, which means utilization of less than 1. In the third stage, we have 2 soil nails, 2 nail rows, and here we are below the factor of 1. 4 nails, 5 nails, and so on. And finally, we have the final excavation stage, where we have the slip circle, which is the critical one, and as well, this is with an utilization factor of less than 1. Here we have an overview of the maximum nail forces for the critical block, which is shown here. This earth block, which starts directly below this force. And in addition to these graphics, we have in detail all the calculation results. First, all the input parameters with the soil layers, with the loads, load cases, and so on, with the list of the nails, the safety factors, and then the iteration of the critical block. So the critical one is here with infinite utilization, because we have no nails yet at this point. And from the next excavation stage on, we have the real factors here, utilization less than 1, which is the critical block here. And this is described for all the excavation stages. And if we go down to the latest step, we have as well the external stability calculations. Here, the internal stability is again fulfilled with a factor of less than 1. And then we have the calculation of the shotcrete wall. So the soil nails are supports of the shotcrete wall. And we have a load for the earth pressure on the soil nail wall. And this wall is calculated, and we receive the required reinforcement for the excavated side and for the supported side. And then we have different nail forces, and we have to use the critical ones, which means we have first a nail force which might be possible. So if a soil nail is very long outside of the critical block, he could transfer very high force to the ground. But this higher force is not always required. So this is the possible force. And here we have the real required force, which is required for the stability of the critical earth block. And on the other side, we have the dimensioning of the shotcrete wall. And here the soil, the nail forces are calculated as the support forces for this wall. And so the maximum of these two forces is the critical one, which is required for the soil nails. And Here we calculate the required diameter for the steel bar, which is used as the soil nail. So we would need a maximum of 60 millimeters for the soil nails to support here the required support force. Then we do a punching failure check. So at the nail heads, if this force can be fixed at the wall, here the verification is okay. So the action is less than the resistance of the nail wall without additional reinforcement. And if this is not sufficient, we get here a result for a certain reinforcement, which is required in addition to prevent punching. For the external stability of the critical block, we have a bearing capacity analysis. Here as well, we have a utilization of less than 1. And finally, the slope stability calculation, where we might need higher nail forces, not in this case, but it might be possible that for the slip circle stability, we might need longer nails or higher nail forces, which are calculated here. And finally, after the graphics of the situation and the slip circle, we have the calculation of the shotcrete wall. Here, the nails define the supports. We have a certain load, and we have a moment, bending moment, and shear force, which is cut at the edge of the nail plate. So we don't have these highest values in the middle of the support. This is cut. We have a certain deformation of the shotcrete wall and the required reinforcement for this wall. And finally, we have an overview of the maximum nail forces and the different utilization levels of the different excavation stages. Here there are some explanations for the tables that we had here before. Here and the explanation for these nail forces.